Okay. Yeah, thanks. Thank you. Yeah, thank you for coming, and thanks again for the invitation. I'll try to be somewhat informal. If there's any questions, please interrupt. If I don't get to the end, I don't get to the end. It's perfectly fine. I want everybody to follow as much as possible. So I'll talk about non-commutative matrix concentration inequalities. Okay. So this is joint. So this is joint with March Boedihardjo and Ramon van Handel. Trying to understand random matrices. Perhaps the simplest example or the most classical example is simply to try to understand Wigner matrices, right? So let's just sort of set notation. Let's take a Wigner matrix. Okay, and let's call a standard Wigner matrix just a matrix G that's D by D and symmetric and with entries IID N0 1 over D. Okay, except of course the fact that it's symmetric, right? So upper diagonal part is IID. Okay, and normally a Wigner matrix or to be saying the GOE would have a bit more variance in the diagonal. For the sake of the kind of things I'm going to talk about now, this is not so important. Again, we know that its spectral density will go to the so-called semicircular law, right? So the spectral density, or the spectrum of G, right, will converge weakly to the semicircular law, right? Will be this nice, the histogram of the eigenvalues will converge to this nice curve between -2 and 2. And a lot is known about these matrices. Right, we know that the distribution of the fluctuations, the gaps between eigenvalues, there's lots and lots that's known about this. And in particular, I mean, one thing we do know is that the spectral norm of G, right, its leading eigenvalue, will be roughly 2. Right, this can be formulated in many ways. Maybe the expected value of this is 2 or smaller or equal than 2. Or in the limit as d goes to infinity is 2, or some kind of concentration or large deviation inequality that the probability that's far away from 2 is very small. And for now, let's not worry too much about this, but that the spectral norm is 2. Again, we in fact know a lot more. Now, the work that I'm about to describe comes motivated by the fact that in many applications, we want to know maybe not quite as much, but about much more general random matrix models, right? So in many applications, let's say that come from, I don't know, statistics, signal processing, various data science applications, and so on. This is often the case. In many applications, right, we want to understand more general models of random matrices. Right, but maybe we don't understand quite as much. We don't need to know exactly the gap distribution, or we don't need to know exactly the large deviation inequalities. We just want to know, say, what is the value of the spectral norm? Okay, oftentimes we want to know things like what's the expected value of, say, the spectral norm of X, right, where X is a random matrix. And in these models, random matrices might have not identically distributed entries, not independent entries. They might have correlated entries, right? They might have, non-homogeneous variances, right? Maybe deterministically, some of the entries have very high variances. The other maybe are 0 or have no variances, say variances or distributions, right? And there is one inequality that is able to do this. Okay, maybe I should say a word why in many applications one care about the spectral norm in particular. Right, think of you want to study some kind of spectral method, for example, right? Then how much the, say, noise in your data is going to affect your spectral method should be related to the spectral norm of the noise, for example, right? And you expect the noise to have some kind of randomness, and maybe the way the noise presents itself in the spectral algorithm is in some complicated way. And so the matrix that you have to understand is some complicated matrix, but that is random because it feeds off of the randomness of the noise. But maybe, you know, the random noise populates this matrix in some complicated way without all the symmetries that Wigner matrices have. And then there is one inequality that sort of does all of this, and this is non-commutative Khintchine. So this is the starting point. And I'm giving you sort of the, you know, as I got to all of this motivated by applications. I'm giving you that sort of that side of the story without much detail. So Khintchine inequality. Okay. So this is due to Lust-Piquard and Pisier, somewhere late 80s, early 90s, I think. And it says the following, right? Let A1, AN be self-adjoint D by D matrices, deterministic matrices. Okay. And G1 through Gn are just Gaussians, right? They're just 0, 1, IID. So just IID standard Gaussians. Okay. Now the matrix we're interested in is X given by the sum from K from 1 to N, GK, AK. Okay, maybe side note, before we state the theorem, right? X is joint, the entries of X are jointly Gaussian, right? And this is an if and only if, in the sense any matrix of jointly Gaussian entries can be written this way, right? X with jointly Gaussian entries and self-adjoint can be written this way, right? Just the same way that, you know, a vector of jointly Gaussian entries can be written as the sum of standard Gaussians times a vector, each one times a different vector, of course. And this can be written this way. Okay, so this is quite general, right? They can have all sorts of dependencies, the entries, all sorts of, right? They can have like variances. Some entries can have variances that are very high. Some entries can be fixed to 0, anything. And the inequality says the following: that the expected value of the spectral norm of X is smaller or equal, up to constants, than square root log D times sigma. Okay, where sigma is a natural parameter for this problem, sigma square is the expected value of X squared. The spectral norm of the expected value of X squared. Okay, so this is the theorem. Okay, so it's a very, very general statement, right? It applies to any I mean, okay, they need to be jointly Gaussian, but it applies to any matrix with jointly Gaussian entries. It doesn't matter if the entries are very correlated. It doesn't matter if right, if some entries are set to 0 deterministically, right? None of this matters. Okay, let me just convince you of two other things. So one, this is a natural parameter. Why? Because if I take, say, the expected value of the spectral norm of X squared, right, we expect the spectral norm of random matrices to concentrate very much. So taking, you know, expected value of the spectral norm squared or square of the expected value should be roughly the same. Right, but now by Jensen, okay, so this is of course equal to, expected value of X squared, right? Now by Jensen, this is bigger or equal an expected value inside the norm, right? And this is exactly sigma square, right? So you expect that the spectral norm of X will be at least sigma. The expected value of the spectral norm of X will be at least sigma. And then non-commutative Khintchine says that this is true also as an upper bound up to at least a root log. Okay, I didn't quite prove that because Jensen would go the other way with the square, but by concentration, this should be the same as the square of like outside of the expected value. Okay. Now, maybe another point to make is that from inequalities of this type, there are ways to get what is often referred as matrix concentration inequalities, right? From this, one can obtain by essentially standard tools like symmetrization and concentration, right? One can obtain what's so-called matrix concentration inequalities. Right? What do these inequalities look like? They basically usually look like things like this. They are for non-Gaussian matrices. They're for matrices that can be written as sums of independent matrices. So you take Z1 through Zn, say, independent and centered. And you give bounds of the type that the probability of the spectral norm of the sum of the ZKs bigger or equal than T, right, is smaller or equal than something. Again, there's many examples of these inequalities, and they can be obtained via, say, non-commutative Khintchine. There's also other ways of obtaining them. Again, these are very useful because in practice, one can write many of the random matrices that show up in applied math and computer science problems, statistics, and so on as sums of independent. Right, and they can look nothing like a Wigner matrix, right? Maybe you have something that has to do with some kind of random graph, a very structured random graph, right? You can write its adjacencies, Laplacian, and so on. Oftentimes, there's sums of independence, but right, they look nothing like Wigner. And yeah, to see this, so Joel Trop has a very nice monograph about inequalities of this type. Okay. So now the talk today is about understanding or improving non-commutative Khintchine. Okay, so let me motivate why one ought to maybe improve non-commutative Khintchine. So it's of course very general, but is it sharp, right? So non-commutative Khintchine, right, is very general. But the question is it sharp? Is it sharp? Is this root log D actually there? All right, so let's go and try the example that I described as being sort of the example that started random matrix theory, these Wigner matrices. Okay, so let's take a Wigner matrix. All right, so let's say Gx is a Wigner matrix. Let's say a standard Wigner matrix. Okay, then what is expected value of X squared? Right, so in the off diagonals, you get the expected value of the inner product of two different rows. This is 0. Even though they are symmetric, this is still 0. Right? They're not independent because symmetries are the same because of the symmetry, but the inner product is still 0. And in the diagonal, what you get is the square of the L2 norm of the square of the L2 norm of a row, right? But each element in the row is a Gaussian of variance 1 over D. And so the L2 norm square will just be 1. And so this is actually exactly the identity. Okay. This means in particular that the sigma parameter of this model X, this matrix X, is just 1. Okay. Okay, and of course, I mean, the entries are jointly Gaussian, so of course we can write it this way, right? There's one AK for each edge, for each pair IJ, and it's just a matrix that has 1 in entry IJ and 1 in entry JI. Right? But non-commutative Khintchine, what would it say? Non-commutative Khintchine would say that the expected value of the spectral norm of X is smaller or equal than square root log D times 1. And so this is clearly not sharp. Right? Right? This log does not belong. Right? And there are many applications right? So this square root log propagates also to in fact, it tends to propagate to a D here in front of the probability in the matrix concentration inequalities for if any of you has ever used them, but it propagates to many applications and you know, non-commutative Khintchine and matrix concentration inequalities sometimes like add have logarithm, or I should say suboptimal logarithm terms. Or factors, I should say, right? Right, so even in sort of the most classical random matrix model, it's not giving the right answer. Okay. However, you know, in general, the log is needed, right? So let me give you an example that the log is indeed needed. Let's look at diagonal matrices. Okay, so let's take X to be the following matrix. It has a G1 here on the diagonal and a G2 and so on, all the way to GD. Okay. And now I put zeros in the off diagonal. Okay. Now this matrix, well, it's easy to see, right, that expected value of X squared, right, is what? Is also identity, right? Because X squared is just the Gaussian square on the identity. Their expected value is 1. So this is just identity. So sigma is also 1, right? However, if I look at the expected value of the spectral norm of X, right, what is this? This is just the maximum of the diagonal entries. Right, so this behaves actually like root 2 log D. So here the logarithm term is needed, right? Here the square root log factor is needed. So it can't be removed always, right? In general, the inequality is tight. Okay, and sort of the guiding principle or meta conjecture, if you will, it's already, you know, for a while of what's going on, maybe perhaps to drop in 2014, around 2014, is that diagonal matrices commute and Wigner matrices do not. Okay. Somehow this logarithm factor is there because things commute, and it shouldn't be there when things don't commute. And I'll try to, one, convince you of this, that this idea has some legs, and two, tell you how to actually exploit this idea to give an improvement over non-commutative Khintchine. So I don't know if anyone had formalized this idea yet, but I learned of this problem from Joel Trop, I think in 2014. And yeah, I've since been somewhat obsessed with it. And let me tell you, yeah, finally we have something to say. And so let me tell you about yeah, let me first give you some inequalities that we do know, then I'll try to convince you that perhaps it does have something to do with commutativity, and then I'll tell you a bit about the proof. Okay, so the goal is to give inequalities, right? So the goal of today, the goal of today is to argue this, that if things are very non-commutative, then indeed there is an improvement. And maybe even before I try to convince you that commutativity has something to do with it, maybe it's worth mentioning that if you go back to the proof, several proofs of non-commutative Khintchine, or proofs of matrix constitution inequalities based in other ideas and so on, somehow you can almost always track in the proof to a point where things are upper bounded by the commutative case. You do something and then you say, oh, the commutative case is the worst case, and then you carry on from there. And somehow what you need to do is to be careful in this step. And if things are not commutative, to show that this step is suboptimal. Okay, but I'll be a bit less cryptic in a second. So the goal of today is the following. So I want an inequality of the following type. Okay, expected value of spectral norm of X, small or equal, up to constants, then this sigma parameter plus some other parameter that hopefully is small for Wigner, times some log factor. Right, this is the goal. And this is to work for matrices that are very different from Wigner matrices, right? We can't do things here by perturbative arguments of starting with Wigner and sort of arguing if you're close to Wigner, the spectrum must still be close to Wigner. Things like this will not work. So what do we know? So we know a few things. For matrices for X with independent entries, but with potentially very, very different variances. So we did this, myself and Ramon, back when I learned about this problem. This is what we could do in the context of this problem. So when Xij is Gaussian with mean 0 and variance Bij square, but these B's, some of them can be very, very large. Many of them can be 0, and the B's are picked deterministically. Right, but say self-adjoint, all independent. Then we could show that the expected value of X is smaller or equal than X plus certain weak variance times square root log. Okay. And here, this parameter, I mean, is easy to compute. It's basically max under J of the sum Bij, or max over, usually I write it like this. It's all the same, but Ij square, right? It's just the spectral norm of the expected value of the, right, of the expected value of X squared. And this term here is much, much smaller. It's just the maximum over all Ij of the biggest one of them. Okay. Now, so in 2014, we got this and tried very hard to go beyond independent entries with essentially no success. I mean, and the proof that we have here really doesn't work for non-independent entries. Okay, so there was another independent progress due to Joel Trapp around this time. I think maybe the paper showed up on the arXiv in 15 of a very different style. So he showed the following. Show that the expected norm of X is smaller or equal than, and so it still has a log D term, but he can make it smaller. And then he has a new parameter. Okay, we call this the matrix alignment parameter. I'll explain later what this parameter is. This inequality really does attempt to capture non-commutativity. This parameter does attempt to capture non-commutativity. The ideas here are key to what we do now. However, this still does not capture Wigner, right? It still has this log D to the 1/4. And this parameter Wx, I'll explain what it is in a bit, because you'll come a bit more motivated in a second, is actually quite difficult to compute. And I essentially don't know how to compute it, or didn't know how to compute it until inequality, for essentially any example. Okay, maybe for Wigner matrices, but that's it. So today, let me just show you the inequality I'll show you today. It's me and Boedihardjo and Van Handel. We'll show this expected value of X smaller or equal up to, I mean, here I can even give you the right constant, the 2, just like in Wigner, plus universal constant, a new parameter, which is actually a way of bounding that W parameter. This will come in a second, but it's one that you can actually use. This mu parameter is the spectral norm of the covariance of the entries of X, right? So can view X as a D square vector. You just take the covariance. So it's a D square by D square matrix, and you take its spectral norm. Okay, and in the end, if there's time, I'll show you a few examples. But if, for example, recovers the independent entries, right? Not with the root log, it's with the log to the 3/2. But it recovers many more general examples with, yeah, it's sharp in many other examples where the entries may be very dependent and very structured and so on. Yeah, I'll try to convince you that this is sort of the, yeah. Right, the two sigma x is really the right answer in a certain way. Okay, I'll as you'll see the proof, you'll see what I mean. Okay, so let me now do to convince you of why non-commutativity has anything to do with this. Let me show you a proof of non-commutative Khintchine. Okay, so let's see a proof. Okay, let's see. Maybe I'll go to the next page so that I have a fresh page. So proof of non-commutative Khintchine. Okay, because in the proof we'll see where the loss happens. Okay, so the idea is to use the moment method, right? To see that expected value of trace of x to the 2p. Right, if we can control this for p very large, we can effectively control the spectral norm. Right? So many of the proofs of non-commutative Khintchine go this way, right? So what is this? This is equal to, right? I can expand the sum inside and I get some nasty, right? Just so that we make sure we're all on the same page. Let me write this out. Right, I get just, right, because x is the sum of gi's, ai's, I just get this. Okay. Now, of course, many of the terms are 0 unless every index shows up an even number of times. Right, and so there's some combinatorics going on here. And there's a very nice way of capturing all these combinatorics, and this is known as Wick's formula. Right, so Wick's formula says that I can write this in the following way. I take the sum over all pair partitions of the 2p elements, right? This is the place where the indices are going to be the same. So over all pair partitions of 2p elements. And now I take all choices of indices that are compatible with that partition, where two elements, if they're in the same pair in the partition, they need to be the same. So f is now a function from the 2p picks, right, for each index, which of the n matrices it receives, and it's compatible with the partition, right? And now I take trace of AF1, AF2, so on and so forth. Okay, if you've never seen Wick's formula, sometimes it's called Iserly's formula. If you've never seen Wick's formula, you may notice that there's some overcounting and some undercounting happening at the same time. Right? There's some overcounting because some indices may be showing up in many partitions. Right? If the same index shows up 4 times, it's showing up in 3 different partitions. There's some undercounting because if the same index shows up 4 times, it should show up with the 4th moment of the Gaussian and not with a factor of 1. You'll notice that this is also 3, the 4th moment of the Gaussian, and this is why this formula is true, because the moments of the Gaussian are exactly this overcounting. Okay, so now comes the commutative is the worst step. Okay, so now, right, warning, we're going to go into the commutative is worse. The commutative is worst step. So if things were commutative, then any partition would be the same. Right? The choice of the partition doesn't matter. And I could just take the partition where things show up, right? There's a very nice way of writing these partitions, which is I can think of my numbers 1 all the way to 2p, and I can just pair them like this, right? Maybe like this, so on. Right, this represents one partition. If things were commutative, all the partitions would be the same, right? Because I can reorder the A's, it doesn't matter. And so I can take the simplest possible partition, which would be this one, say. Right, but what would this one correspond to? This one correspond where the AK shows up with another AK. So all the A show up as the square. Right? And so one way to formulate this is that this term is an absolute value, always smaller or equal, then the term that corresponds to the partition, that simplest partition, right? Or you can think of, if they commute, the term in which I group all the A's, the same A's together. So I get instead trace of the sum of AK square to the power P. Right? Because if I take this trace this way, then I get exactly the, right? Then I get exactly this product for when the sum overall overall possible choices of index, or when we're in the partition, this partition here. Okay, so this stated, without any constants and so on, it's due to Buchholz. In 2001, but it's commutative is the worst kind of statement, right? You would expect that if the A's are very non-commutative, then this product, when you get an A1, and then you wait a while until you see another A1, by the point you get there, somehow your eigenvectors have been rotated, and so you should see a smaller trace. That's the guiding principle. That's the intuition. Okay, so now with this, we're almost done with the proof, because now this means that this is smaller or equal than the number of pair partitions times the trace of sum of AK squared to the P. Okay, and we're basically done. Why? Because how many pair partitions are there? Well, to the first one, I need to pick one of its friends. I have 2P minus 1 options. Now I go to the next one that's free. I need to pick a friend for it. I have 2 less options. Right, so every time I have 2 less options, so this is smaller or equal than 2P double factorial. Right, and here what do I have? Well, the spectral norm of the sum of AK squares is sigma square. To the power P will be sigma square to the P. And I have a trace, so I have at most D. Okay, but now by Jensen, right, just by Jensen, the expected value of X, right, is smaller or equal than the expected value of the trace of X to the 2P, right, 1 over 2P, right, but this is smaller or equal than 2P double factorial to the 1 over 2P times D to the 1 over 2P times sigma, right? I need that D to go away, so I need to take P to be something like log D, right? If we want to see the spectral norm of the matrix, we need to take it to a power that looks like the logarithm, right? And this term looks like root P, right? If I do that, then I get that this smaller or equal up to constants, right? Because this guy here looks like square root P. And so I get up to constant square root log D sigma. Okay, so what was the problem? The problem is that there are too many partitions, right? The number of, so what was the issue? Is that in general, there are just too many partitions. It's too large. And somehow most partitions should have crossings, right? Partitions that look like this, there should be a lot less of them, right? In particular, look exactly like this is only one. But turns out that the right way of capturing the issues in non-commutativity is not just to ask that they do like this, but it's the so-called crossings, right? So sort of good partitions or partitions that will create big terms are partitions in which the AK show up together. So are things without crossings. I mean, this is what free probability studies. Okay, say things like this. So no crossings. And here you have partitions with crossings, right? Okay, and the idea is twofold, right? And this idea was already in Trop's work, is to try to make the following program, right? That there are a lot less, right? There are a lot less partitions without crossings. And partitions with crossings should contribute a lot less. Partitions with crossings should have more cancellations. Okay, and it's indeed, I mean, Joel Trop wasn't really using this proof, was using a different argument, but similar in spirit. And this is really what he tried to exploit, right? This is the program that he tried to carry through. And okay, one part of the program is easy because the fact that there are less crossings, less partitions without crossings, this is a very well-known fact. The fact that partitions with crossing there should be more cancellations for those is not clear, and it's not clear how to measure this. And this is exactly what this parameter, this matrix alignment parameter tries to capture, right? And now will be a lot more clear what this parameter is trying to do. Right? Particularly, maybe let me write this way. What is something with a crossing is where you have something like a trace of AI. And then you have a bunch of stuff in the middle. Then you have maybe an AJ, a bunch of stuff, an AI, a bunch of stuff, and another AJ. Right? Then the AIs and the AJs cross each other. Okay. So Joel came up with this nice, very nice idea of bounding crossing terms by this. Or, yeah, I should say of trying to measure how much the A's have non-commutativity this way in the hope that you can bound the terms with crossings by something involving this parameter. Okay, so, right, you sort of have to, I mean, it looks a bit like the thing I wrote. You have to maximize over unitaries in the middle. And this is really one of the issues with this parameter. Right, and this is how you obtain that inequality involving this parameter. This is actually quite difficult to compute, right? Because you have to maximize over these unitaries. This is quite tricky to compute. So what's our idea? Okay, so idea for today. Instead of trying to go into this proof or the integration by parts proof where you just integrate by parts and try to build a recurrence and try to bound the terms with crossings by something involving this, which seems to not give quite the right answer. The idea for today is, what if we just change the model? So what if we change the model to force non-commutativity? Okay, and really what we want to force is not non-commutativity, is freeness. Okay, so there's an area of mathematics called free probability, which studies non-commutative random variables and has a notion of free random variables. And free random variables are exactly variables where if I have an expectation, like here, of a product, if there are crossings, then its expectation is 0. Right? They're like maximally non-commutative in the way of freeness, like a group, like the free group of having no relations. Okay? And so the idea is to use these ideas of free probability Okay, but I'm going to now describe the free probability very, very briefly, and then I'm going to get into something that's actually finite dimensional. Okay, this is a theory due to Voiculescu. Okay. And so in free probability, there's the analog of Gaussians. Okay, they have, so you take S1, Sn to be what's called the free semicircular family. Think of them, they're like the Gaussians of free probability world. The free semicircular. And now I'm going to change my model. Now I'm going to take my model X free. Okay. Instead of taking Gaussians, I'm going to take my AKs or AIs, and I'm going to take the tensor product with these random variables. Now I'm making every term with crossing be 0 by design. This is a completely different object. Okay, in particular, it satisfies a Wick's formula. Right now, because these things are in infinite dimensions, I should really use the normalized trace, but it satisfies a Wick's formula, right? Okay, since I don't have a lot of time, let me write just here. It says it satisfies a Wick's formula, where if I replace this by free, okay, right, then I would get the S's here, and basically the Wick's formula would be, instead of this, I would get V just on non-crossing partitions. Okay, so only partitions that don't cross. Okay. And now the number of partitions that don't cross is a lot smaller. And in fact, I mean, it's like the Catalan number, so it's smaller or equal than 4 to the p. Right? And so if I carry out this argument, I get a 4 to the p here, but I get a 4 to the p to the 1 over 2 over p. I just get a constant and the logarithm goes away. Okay. So for this term, all the non-commutative, all the crossing partitions disappear, and I just have to carry out the first part of this program, which, I mean, it's classical, right? This is the whole idea of free probability, which is by now a relatively classical field, and I don't have to do the second one because it's already done by design. Okay, so of course I'm not solving the original problem, right? But let me make this now finite dimensional. Let's go back to finite dimensions, and let me define Xn to be. I don't take a semicircular family, I just take Wigner matrices. Right? These are standard, these are IID, standard Wigners of dimension n. Okay, so now these are just matrices of large dimension, but they're finite dimensional objects. Right? In the limit, as n goes to infinity, they go to that, right? This we know. So as n goes bigger and bigger, they start looking a lot more like the non-crossing partitions matter. Okay. And now the idea is to do interpolation between this and my x. Right? The idea now is to do Gaussian interpolation between this and my x, like my original x. Okay, so it's not quite with it's not quite with x. It really is with this other, I have to create this other auxiliary variable, but this is more just details, where I place a diagonal matrix of dimension n with independent Gaussians in the diagonal, and I should write the order the same way. Okay, but the moments, right? The normalized traces of these matrix look the same as the top, because this just contains a bunch of IID copies. It's just a block matrix whose diagonal blocks are a bunch of IID copies of the thing on the top. Right, and now I can call this x0, and now the idea is just to do Gaussian interpolation between these two matrices. And just to argue that, say, things like normalized trace of the matrix to the power 2p doesn't change very much going from one to the other. And how do we bound this? We bound this exactly with this parameter w. Right, exactly, where is the parameter w? Sorry. Exactly with this parameter w. Right, and if we have a way of bounding the parameter, although we have to bound the parameter w not of the original matrix X, but in fact of this auxiliary matrix, and then we have a way of bounding the parameter w with this parameter that I showed you the inequality of, with this parameter, the covariance of the original matrix. Okay, so now I'm running out of time, so I don't want to take more time than I have. Let me just, so I could mention a few examples. I could also mention some open problems and lower bounds, so impossibility results. Let me instead mention very briefly just how this is much more general, because you're doing interpolation, you don't have to do just traces of x to the 2p, right? You can do it for resolvents and so on. So you actually get statements of the time. The spectrum of x is inside the spectrum of x free up to, so x free, sorry, right? Up to epsilon provided, right? Usually these things is provided that this parameter is a lot smaller than sigma x. Where a lot smaller, it just needs to be small by a factor of log, right? Where in Wigner is smaller by a factor of root d, right? You get the same thing for polynomials. So you can prove things like, it allows you to prove things like strong asymptotic freeness of, as long as Vx is much smaller than sigma x, you get asymptotic freeness of your matrices. And proving asymptotic freeness is, for general models of matrices is a challenge. And of course, I mean, with just standard tools, you can get concentration inequalities or matrix concentration inequalities. Right? I won't write them here. You can see them on the paper. Right, where you have sums of independence, and you can write concentration inequalities that exploit freeness. Okay, and I mean, maybe if there's questions, I can talk a bit about some open problems and some certain lower bounds. That's what I didn't have time to do, or examples. Okay, thanks so much, and sorry for the extra minute.
Okay, thanks very much. So I'll stop.